Hi, Gen Chem 1 students. This is our pre-lab video for chemical reactions week 2. So we started this experiment last time we were in lab by doing a whole bunch of double replacement reactions. If you don't remember what that means, make sure you go back to the playlist that I linked in the pre-lab from last week and check out the videos about types of reactions. Then the other skill you should be working on between week 1 and 2 of this experiment is balancing reactions and figuring out the states of matter. So again, that playlist has videos on both of those topics as well. So you want to have completed your best guess for what the reactions are for the worksheet, which I think we're on pages 99 through 104 of the lab manual. That's due when you come to lab. And remember, I'm not looking for the perfect answers, right? So you should not use the internet. You should just try your best to get the reactions balanced correctly. And then what I'll do is if there's answers for every one of the reactions I asked you to do, you get full credit for the worksheet draft, essentially. Then in lab this week, as you're working through the rest of chemical reactions, I'm going to come around and we're going to look at it together so that you'll know what you need to fix between this week's lab and when the final report is due, which is really just the packet at the end of the experiment in the lab manual. So yeah, it's going to be pages 99 through 104 that are due in lab when you come in this week. And then there's a couple of more pages after that that you'll have to finish between this week and when you turn in the complete draft before we do experiment 8. Okay, so I want to go over a couple of things that are not in the playlist that are going to help you out in figuring out that last little bit at the end of the worksheet. Okay, so before you come in this week, you're going to need to attempt everything from this page. And again, the same playlists are linked here that I linked in Bright Space announcements last week, all the way through page 104. So some of these reactions we haven't observed yet. That doesn't mean you can't write a balanced chemical reaction, okay? So you're going to want to use this handout that I gave to you along with the one that you fill in some information. That's going to help you figure out types of reactions. If you know what type of reaction something is, it's a lot easier to write a balanced chemical reaction. So for example, for combustions, which we're going to perform this week in lab, you can write the reaction before we measure, anything, before you try it out or observe anything. Because we know that a combustion reaction is going to produce fire, which is a combination of heat and light, of course. And so this worksheet tells you to expect a fuel of some kind, which is a hydrocarbon, and some oxygen. And so you can look up here how there's an example of what that looks like as a balanced chemical reaction in general. So we're always going to have oxygen as a reactant and produce carbon dioxide and water vapor. The specific example is the balanced reaction of how methane burns, right? So use this to help you figure things out, as well as the playlist going through all the balancing reaction steps, solubility, all that stuff. Okay, so some of these reactions you haven't done, but you still need to complete all of the balanced reactions from 99 to 104 in the lab manual. Then, after we do this experiment this week, we'll be able to answer the questions that begin on page 105 and they go up to 109. Okay, and so that's sort of what's due in class this week and next week for the chemical reactions experiment. Now, how do we do balancing reactions and yields and all this kind of thing. So I'm going to do an example of something we're not actually measuring, and you can use that to help you answer the pre-lab questions and to do some of this work here. Okay, so I'm going to make up a reaction. I don't think it's one we do in this experiment, but it's a good example of how to approach these problems. So let's say that the procedure says to react sulfuric acid with barium, that's an R, acetate. Okay, and let's just pretend like we weighed the amount of barium acetate sample before it was dissolved in solution. And let's just pretend like we had 5 grams in our example. The procedure would indicate, in this case, that sulfuric acid is in excess. That means I have more than I need. So I don't need to calculate anything about sulfuric acid since there's extra anyway. The only thing that will determine how much product we make is how much barium acetate there is. In our alum recycling experiment, I don't know why the resolution on my writing is not great today. Sorry. I use a tablet. But the alum reaction, the limiting reactant for that is always the amount of aluminum that you started with, the stuff you cut up. So the amount of everything else like KOH, what do we use? H2SO4, those things don't matter. All that matters is the amount of aluminum. So we're going to kind of use that mass that you measured to figure out how much alum could be made. In order to do that, of course, you've got to have a balanced reaction. So I have a video showing you how to take our 4 separate reactions and put them together to get an overall balanced reaction. You should check that out if you haven't seen it yet. Anyway, for our made up example here of sulfuric acid with barium acetate, the first thing I need to do is to translate what those things mean, right? So whenever we see the ic acid ending, that means that it comes from something where the ending was ATE. So I would want to look on the back of my periodic table and find where sulfate is located. That helps me to figure out what formula to write down. So SO4 2- is a sulfate. The acid part means that I must have some hydrogen in the beginning of this reaction here. So in the beginning of this formula, rather. Hydrogen will always have a +1 for our purposes. And so in order to make the H plus balance out with our sulfate, and I'm imagining that Java program that I linked on the notes and showed you in class where the puzzle pieces come together, you could use that to figure this out. But that's kind of the visualization I have in my head. What I need to make sure of is that my positive charges and negative charges balance out, right? And so I'll need to have 2 of these H pluses connected to the sulfate. I would write that as a chemical formula, H2. I'm going to try to keep it color-coded for you. You don't need to do this. It's just a way to visualize the reaction. So H2SO4 is what sulfuric acid is. And the other thing I need to have is a state of matter. So acids are always aqueous. That's a requirement in order to use that word acid, has to be dissolved in water. So that one's pretty easy to figure out. Okay. So far, so good. The next thing to figure out is what is barium acetate. So barium is one of the elements we have to know the symbol for. It is Ba, and because it's in a compound, it's not an element anymore. It's going to be a 2+. Actually, I'm going to write it up here. So that's our cation for our second compound. The anion is acetate, and again, that ATE ending should clue you to go either ATE or ITE are only going to be on the back of the periodic table. So we want to look there and see what is acetate. Turns out there's two different ways to write the formula for acetate. Most people in Gen Chem are probably going to choose C2H3O2 minus 1. You can also write it like this. They're both the same thing. The difference is just that the second version shows the structure, how things are connected. So these two oxygens are connected to that carbon. So we did that in lab when you made acetic acid at the Vesper experiment. But either way you write it, it should be fine. So we notice that there's a +2 and a -1. We have to combine these together in a way that balances those charges. And so I have more positive than negative. That means I'm going to have two. Oh, that's a highlighter. Here, I'm going to have two of these acetate pieces. I'm going to show that in parentheses, and you could write it as either C2H3O2 or CH3COO. Either one is cool. I need two of those, so I'm going to end my parenthesis and put the two outside of that. The parentheses here are required because that polyatomic group has two separate particles attached to this barium. If I didn't have a parentheses here, it would look like there were 22 oxygens. Okay, so essential to have that. Now, in order to figure out the state of matter for this one, we would have to go look at our solubility chart. Acetate is one of the things that is always soluble, so this will be dissolved in water, no matter what it's attached to. Anytime we have C2H3O2, it's going to dissolve. Okay, so those are our reactants. To figure out the products, what I like to do is just take the cations and switch places. So I drew my cations in purple to help me do that. If I have a hard time visualizing things, one way to handle this is to get some Post-it notes of different colors. Maybe your cations are always orange and your anions are a different color. And you can write them right on here and pair things up physically using Post-it notes. I find that to be really good strategy for a lot of people. So if sort of on paper's not working for you, try Post-its. But anyway, so I have my BA2 plus Post-it and I have my H plus Post-it. They're going to switch places. So if I take my H plus and I pair it with the acetate, and I take the barium and I pair it with the sulfate, that's gonna be our products. This is a double displacement reaction, and I know that because I'm starting with two compounds and gonna make two different compounds in the end. Okay, so then if I take my H plus and connect it to acetate, H plus and acetate is a 1-. That means I just need one of each thing. You can keep color coding if it helps you. And then to pair up the barium 2+ with the sulfate, that's a 2-. I also only need one of each of those things. Now you'll notice I'm not paying any attention to the left-hand side of the reaction. I don't care that I have two acetates here and two hydrogens here. What I care about first is making these real compounds. So I make sure I have a +1 and a -1, a +2 and a -2. Those have to be balanced before anything else can be corrected. You cannot balance the entire reaction and figure out your products at the same time. You have to figure out products first thing. So we know our products now. I just need to state. We said a second ago that acids, anything with an H in the front, are always going to be aqueous. So that's true for this HC2H3O2 because this H is a cation. It's the H plus there. And so that makes this acetic acid, same molecule we made a model for in the Vesper experiment. It has to be AQ because it's an acid. For BaSO4, this one's interesting. So if you go look at your solubility chart, you're going to see that sulfates most of the time are soluble, but when I put them with certain things, they do form a solid. Barium is one of those exceptions. So barium sulfate is actually going to be a solid. Now, our last step is called balancing the reaction. Okay, so first we had to translate from words to formulas. Then we had to figure out states of matter for our reactants. Then we figure out our products and their states of matter. And our last thing here is to make sure that we are not creating or destroying anything. So that's states of matter. I'm going to do this with a green color, so it's different than what we have here. Now, when we balance chemical reactions, sometimes you'll see advice to look at each element individually. I find that that takes people longer. I recommend if you have polyatomic groups like sulfate and acetate, that they should just stay together because most of the time that's what happens chemically. So I'm going to just kind of make a list. Generally, I start with metals first. So in this case, that's a barium. Then I'll look for non-metals. That was the only metal is barium, so I'll put that on there. We have a sulfate. It doesn't matter which order you do sulfate or acetate in. And then the last thing I have here is my hydrogen ions, okay? So in this case, double displacement reactions don't have a change in charge. So I can write the charges here while I'm balancing and it will be just fine. So I have one barium on the left and I have one barium on the right. So that one's good. I have a sulfate on the left and a sulfate on the right. So that one's already good. Acetate. I have two acetates because of this subscript. Over here, I've only got one acetate at this time. In order to make that balance, I cannot change anything about these subscripts at this point. Once I figure out my products, I can't change the product. All I can do is modify the coefficient in front of that particular product. So if I need two of the acetate, I have to put the two in the front. Now that's balanced. I have two acetate on both sides. Hydrogen, I have two here. And now because I have a two coefficient, it will apply to the hydrogen and the acetate. So hydrogen's already balanced. Often I wait to do hydrogen until the end because it will automatically balance that way. If I started with a hydrogen, sometimes that can cause a little bit more back and forth correction. So the order to do it in that minimizes the work is metals, non-metals other than oxygen and hydrogen. Oxygen is included as a polyatomic, but that's okay, right? And then we'll do hydrogen last. That's sort of the process, okay? So now our reaction is balanced. So overall, I'm going to just rewrite it to keep us tidy. Overall, we know that we have one sulfuric acid. It's going to react with one barium acetate. Those are both aqueous. And we're going to produce two acetic acid, which is also aqueous, and one barium sulfate, which is a solid. That's the foundation for everything we would want to know about this reaction. So that's why we have to learn how to balance things. It's kind of like if you're baking and you don't have enough of a particular ingredient, say eggs, then you can adjust the proportions of everything else based on how many eggs you have. Similar idea. So we already said that sulfuric acid is in excess. Our abbreviation for that is literally just XS, but it's excess, the word. This is our limiting reactant, and we had started with 5 grams of that material, okay? In order to figure out how much of our product we can make, in this case, it's going to be the solid because that's what's easy to filter out and weigh. We need to start from 5 grams of barium acetate. And the only way to figure out how much product can be produced is to convert things so that they are in the same kind of unit. So grams of barium acetate are not equivalent to grams of barium sulfate because they're different particle sizes. So we have to go through moles in order to figure out relationships between whether I'm trying to figure out how much product is there or how much reactant gets consumed or whatever, I have to go through moles. So our first step here will be to figure out the molar mass of barium acetate. So of course we need the periodic table to do that. Barium is 137.328. And you should show this work in case you make a mistake. I can give you some partial credit. I have 2 carbons, and each carbon is 12.011 grams per mole. Anytime I'm using the periodic table, it's going to be grams per mole. Some of you have a habit of just writing grams. That's not actually accurate. The definition is grams in 1 mole, so we want to make sure to include grams and moles. Plus, that's the only way it makes sense as a conversion factor. And then I have 2 oxygen. Let me not round. I was going to round. I'll keep all the digits on the periodic table because I don't want that to be what limits accuracy. Okay, so we have 2 acetates, and so this whole thing here should be multiplied by 2. You could achieve the same thing if you do this. If you go 4, 6, 4, that's also okay. Whichever way you're comfortable is fine with me. Just make sure that you have the right coefficients, your correct total of all of your atoms when you are figuring out molar mass. Okay, so our answer for our molar mass here is 255.368. Grams per mole. I did not round anything. I kept all the digits, and I recommend doing that from the periodic table data. Now I can take those numbers and put them into the right spots to cancel grams of barium acetate and get it into moles of barium acetate, which is 0.0195796. Your calculator might have more place values. I'm just using a TI 30, so it doesn't have as many digits. But I need to keep at least 4 significant figures because I have 3 sig figs in my original mass. I try not to round at all if possible, which requires using the answers in the calculator. So that's how many moles of barium acetate there are. Our next step will be to convert from moles of barium acetate into barium sulfate, right? And so we're going to use this balanced reaction. We can see in this balanced reaction that we have 1, that we don't usually write a 1 there, but you can. We have 1 barium acetate for every 1 barium sulfate. So this is pretty easy to convert. I don't want to skip showing this step in case I balanced my reaction incorrectly. And I want to really demonstrate an understanding of dimensional analysis. So we're going to make sure that even if the ratio is 1:1, we always show this step. It comes from the balanced reaction. I don't need to have a parentheses there. If it helps you understand the polyatomics, you can do that, but I don't need it. So we've canceled a unit here, right? We canceled moles of barium acetate. This is called a molar ratio, and it is like one of the most influential parts of chemistry. It does not change the numerical value at all, but it does change the meaning of what we're looking at. Now we have moles of barium sulfate. In other words, we have a unit about our product, which is what we were trying to do. Our last step is going to be to convert from moles of barium sulfate into grams. And so again, we have to figure out the molar mass from the periodic table. So 137.28 for the barium. Sulfur is 32.066, and I only have one sulfur. Oh, and by the way, if you like to do this like vertically instead of horizontally, that's perfectly fine. I don't care. I do need to see the work and the unit, but whether you organize that horizontally like I have or vertically, it doesn't matter to me at all. All right, so we have, for this molar mass, we end up with 233.342 grams per mole. Now, I'm in moles up here, so we're going to put moles on the bottom. Grams is going to go on top. So I don't need to flip this one over because the units will cancel appropriately already. So now we've canceled moles and we get it into grams, which is called a yield. This is a theoretical yield because it was based on the initial material we started with. So our theoretical yield, which I'll abbreviate as TY, our theoretical yield here is 4.56874 grams of barium sulfate. It's worth noting here, you'll see I have written the chemical formula on every single step. It's part of my unit. That's going to really, really help you out in chapter 7 and everything after that. If you don't do that, often people will skip the molar ratio step, which can have really big impacts on your final answer being correct. I also want to think about significant digits, right? So back in the beginning of this, we started with 5.00 grams. Your actual numbers from alum are going to have more significant digits, but that's what I have in my example. And so we would want to round to 3 figures here. So 568 is going to round to 57 grams of product. That's our theoretical yield. Okay, that's in theory how much should be made if everything works out perfectly. We know from our experience with error so far in this year's work that nothing is perfect, and that's normal. So we'll have errors like transfer loss or perhaps contamination from water or whatever. So we would need to weigh an actual amount of product, and most of the time that is going to also include like the container that you weigh it in, maybe even filter paper, and so we need to remember to subtract those out. That means you have to measure the container that you're collecting your product in. Sometimes that's a watch glass, sometimes it's a beaker, kind of depends. And you're going to need to weigh the filter paper before you get it wet. So I'll take the total mass of all of that, subtract the container and the filter paper, and let's pretend like I got exactly 4 grams of product after I subtract all of that stuff. We can use that information and the theoretical yield together to calculate a percent yield. So a percent yield is just the actual amount you got divided by the theoretical that you calculate times 100%. So in this example, my percent yield would be 4 grams on the top divided by our expected, which was 4.57 grams. Notice this is the same chemical. Both of them are about BaSO4. And don't forget to multiply by 100%. So I end up with a percent yield of 87.5273, and it keeps going. I'm going to round to three significant figures, which is 87.5%. So to give you some context, that means I basically made the majority of the product I expected. So that's not too bad for a Gen Chem 1 level of experience, right? I probably had transfer loss because I have less than 100% yield. That's really common when I filter anything. It's impossible to get every little bit into the filter paper. Um, I would not say that I have error around contamination because contamination would only be indicated if I have more than 100% yield. Okay. So think of percent yields kind of similar to a test grade. You want 100%, right? That's optimal. If it's less than 100%, that means you lost some material somewhere. Either it didn't fully react at some point or you have transfer loss, something like that. If I had a yield over 100, then I want to start thinking about, did I really dry out all of the water? Or was there maybe, did I not subtract out the full weight of the filter paper or something of that nature? Okay, so we want to use our results to write a valid conclusion that explains why we have the result we do. Even if I got 100%, it's probably not actually 100%. I might have a combination of different errors that contribute to that. And I just got lucky, right? It doesn't happen often, but sometimes it does. If I were doing this as a professional chemist, say if I worked in the pharmaceutical industry, we would not normally, as a society, companies don't allow reactions with yields less than like 99% because pharmaceutical medications especially are made in multiple steps. And so each step needs to have a high yield because low yields mean we're losing money in by not having all of our reactants making product, right? So as professional chemists, as chemical engineers, you learn to get better yields over time. But in Gen Chem 1, if I had an 87.5% yield, that's pretty good. It's pretty good. So that should give you maybe just a sense of scale here. Um, so go ahead and try the pre-lab questions. And if you need help, make sure you come to office hours or send me an email.